Hello, welcome everybody. In this video, we're going to talk about alkynes, and this is going to go over two parts. So this is part one. And we're basically going to talk about naming, preparing, and reactions of alkynes in this section. First of all, let me just remind you the alkyne has 3 bonds. If you want to really kind of think about that in terms of orbitals, which is always a good idea with organic chemistry. The first bond is a sigma bond here. The second bond is a pi bond. So here you can envision 2 pz orbitals overlapping. These arrows indicate electrons. 2 electrons make a bond. And then the other py orbitals overlapping here. That'll be your third bond of the alkyne triple bond. So alkynes are very reactive. You can do a lot of different types of reactions and synthesis utilizing the triple bond because it basically has 2 pi bonds of high electron density. So we already know alkenes are very nucleophilic, can attack an electrophile, the same with alkynes. And in fact, you're going to see a lot of similarities to last chapter's reactions with alkenes compared to alkynes. So first, a little bit about nomenclature. Basically, it's going to be very similar to naming alkanes with a few modifications. So first of all, the parent chain may be determined a little bit differently. If you just have an alkene, you select the longest chain. However, with alkynes, the parent chain is the longest chain containing the triple bond. So here your parent chain is heptyne, and the chain ends in -ine. As usual, you would identify and name and number the substituents. What you want to do, though, is number the chain so that the alkyne gets the lowest possible number. So you would start numbering on the side closest to the alkyne, 1, 2 here. So if you have these 3 substituents, 3 methyl groups, you get 5,5,6 trimethyl and 2 heptyne. Alternatively, you could put the 2 before the ine, just like with alkenes. What if you have an alkene and an alkyne? Basically, the naming goes with the alk part of the parent chain, the number of the location of the double bond, and then ene, the number of the location of the triple bond, and then ine. Let me give you an example. If you have this compound here, you want a number so you overall get the lowest numbering. So we would number 1 starting from the side to give 1 and 4 numbers instead of 2 and 5 numbers. So in this case, the numbering is based off of the red. So we would have E because of the E geometry here. You have 6 in the chain, so it's hex. And then you give the ene part number first. So it's 4 ene, 1 ine. E hex 4 ene, 1 ine. If there's a choice, whether or not you have substituents, if there is a choice between giving the double bond or the triple bond the lowest number, both could have 1 here, priority is given to the double bond. So the numbering is here, starting with 1, 5, 5 dimethyl, oct, 1 ene, 7 ine. So notice, even though the substituents could have gotten a number lower here, the priority lies with giving the double bond the lowest number. Some other common names are based off of acetylene, the most basic alkyne here. If you have, say, 1 methyl group off of it, you might hear methylacetylene, diisopropyl-acetylene. In one of your guys' labs, you guys will be utilizing diphenylacetylene. Other important terminology, an alkyne at the end of a chain is a terminal alkyne. One that's flanked by carbons is an internal alkyne. Okay, let's talk about the preparation, how these guys are made. Basically, you could take a dihaloalkane, hit it with strong base, and generate the alkyne. Here's the mechanism. You could take a base, deprotonate, the two electrons in this sigma bond will come to form a pi bond, and then it'll kick out the bromide. That would give an intermediate bromoalkene. You can do it again, deprotonate with a base. The electrons here in this bond will go to form the triple bond, kick out a bromide. This is called an E2 mechanism. It's elimination bimolecular, and basically it's happening in one step. You do need a strong base to do this, so we usually use sodium amide here to carry out the elimination. So you need 2 equivalents at least to deprotonate and kick out the bromide. That gives this alkyne product. However, if you still have some of the sodium amide base floating around, it's just going to automatically deprotonate this to give the alkynide anion. So this is actually a really useful intermediate. You can consider it a base, but it can also be a nucleophile. It can attack electrophiles. And what we'll see later with reactions with alkynes, this can actually attack alkyl halides and allow for alkylation off of this carbon center. Practically in the lab, what's done is to just reprotonate this, and we just do what's called an aqueous workup. And all that means is you add water. So if you're in the lab, you literally just drip in water with a pipette or pour in water, and that alkynide ion will get protonated just because water is a stronger acid than the resulting acetylene product. So if you look at the pKa's, these guys are a lot higher than, say, water. So the higher on the pK scale, it'll want to have its H. And basically, the water will be deprotonated and leave hydroxide as a base. Okay, let's talk about the reactions now. In today's video, I talk about hydrohalogenation, halogenation, as well as hydration, very similar to the alkenes, so this is a good review. So hydrohalogenation occurs, as you recall, through Markovnikov addition. Basically, the pi bond will break, add an H, and you reveal the more substituted carbocation. Then the halide will come in and attach. So in this reaction with alkynes, what you get is a haloalkene. If you have excess HX, which could be HBr, HCl, what happens is it occurs twice. So you get what's called a geminal dihalide. Geminal meaning both on the same carbon. The mechanism is shown here. The pi bond breaks, adds hydrogen, protonates it basically, and kicks out the halide, and then the halide comes in. So you have this intermediate vinylic carbocation. This is very unstable, so this will react very quickly to generate this vinyl halide here. If you have excess HX, you will get your dihalide. However, as we've seen in preparation of alkynes, you can take these sort of guys and hit it with the sodium amide, aqueous workup, and you can prepare alkynes. The second type of reaction is halogenation. So if we treat this alkyne, which has 2 pi bonds, with excess halide, you can generate a tetrahalide compound. These occur in reasonable yields, 60 to 70% yields in the labs. This generally occurs with chlorine and bromine. And so if you added just 1 equivalent, however, you could stop at the alkene product. So you would have this dihalide compound, but still remain at the alkene stage. So alkene halogenation, that proceeds via an anti-addition. This one, we're not too sure. We do get a mix of syn and anti. The mechanism's not fully understood. The last type of reaction I want to talk about in this video is acid-catalyzed hydration. Similar Markovnikov addition. The one thing to note is hydration is not going to occur as fast. The only reason is because when you try to protonate this alkyne, you do have to go through this vinylic carbocation, which is not very favorable. So there is a high activation energy. Just envision a energy diagram. You got to climb a really big hill to get up that. It can happen though, and usually mercury is used as a catalyst. What you can envision is protonation, carbocation formation, and then an OH comes in. You get this enol species that's not isolatable just because it quickly converts to a ketone form. So I'm going to show a little bit more detail in that. But basically, overall, what you need to observe is for an alkyne, when you undergo hydration, you don't get an alcohol product at the end, you get a ketone. On the side, that's closer or that's on the more substituted carbon. Okay, involving the mercury, the mechanism is as follows. So you attack the mercury, you get mercury plus here, and you reveal this vinylic carbocation. Water will then come in. You have O2 plus now attached. And as we've seen before, anytime you have this kind of water coming in and you have this plus charge on the O, another water molecule can come in and pick off an H and return the lone pair to oxygen, giving the alcohol intermediate. Then what's going to happen is now with your enol, the double bond here, the pi bond, will then get protonated. And you can envision two types of resonance structures. So you can get this guy where you have the open carbocation, but since it's a lone pair here, you could form the double bond, which is preferred. This will be a major contributor just because all octets are filled. The other thing that will then happen is mercury leaves, revealing this enol here. The enol can then fully tautomerize. That's the word that we use when you protonate this pi bond again. So now we're just going through a process where we're formally forming the ketone. You can see these two different resonance structures. Water will pick off an H plus to give this ketone product. So the interconversion between the enol and the ketone, we call that Keto-Enol Tautomerization, and the enol and ketone are tautomers. The equilibrium does favor the ketone product. You actually will see this in some of the biochemistry chemical cascades if you're taking biochem. So overall, just as I mentioned, just remember when you do this sort of hydration with an alkyne, you don't get the alcohol. You should envision an alcohol OH forming here, but then you get the tautomerization to give the ketone product. So that's when you have a terminal alkene. It's very clear you get this ketone with a methyl at the end. If you have an internal alkyne, sorry, I hope I said alkyne here. If you have the internal alkyne and it's unsymmetrical, meaning the R's are different, you can end up with a mixture of ketones. So you can have the OH add here, reveal a ketone closer to the left side near R, or you can have the OH add on the right carbon closer to R prime, revealing the ketone on this side. Those are two separate compounds, so you can get a mixture of both. Okay, that's where I want to end here. That's where I want to end today. Tune in for part 2, and I will check in with you guys later.